Have you ever wondered why even the biggest tech giants suffer from random, inexplicable downtime? You build a system, you test it on your laptop, and everything works perfectly. But the moment you deploy it across a cluster of servers, the chaos begins. This is the reality of distributed systems. Unlike a single machine where components are physically connected on a bus, a distributed system is a collection of independent computers communicating over a network. This introduces what we call non-determinism. In a single-threaded app, if A happens before B, it always happens before B. In a distributed system, network delays, CPU spikes, and hardware glitches mean that the order of events is never guaranteed. We are moving from a world of certainty into a world of probability, where random failures are actually just complex interactions we didn't account for.
The first reason these systems fail is the network. We often treat the network as a reliable pipe, but it's more like a crowded, unpredictable highway. Peter Deutsch famously noted the fallacies of distributed computing, and the number one fallacy is that the network is reliable. It isn't. Packets get dropped, routers reboot, fiber optic cables get cut by backhoes. But the hardest failure isn't a total outage, it's latency. When a request takes 10 seconds instead of 10 milliseconds, the calling system doesn't know if the message is lost, the receiver is slow, or the response is on its way. This ambiguity leads to timeouts, which lead to retries, which often make the problem even worse. You aren't just managing data, you are managing the physics of light and the fragility of hardware across hundreds of miles.
Then we have gray failures. A clean failure is when a server crashes and stops responding entirely. Your load balancer sees it's dead and stops sending traffic. Easy.
But a gray failure is subtle. This is when a node is technically up but performing poorly. Maybe its disk is failing, causing slow I/O, or a memory leak is triggering constant garbage collection. From the outside, the node looks healthy to a simple ping, but it's actually poisoning your entire system. These sick nodes can cause upstream services to hang, tying up connection pools and causing a domino effect. This is why observability is different from monitoring. You don't just need to know if it's alive, you need to know if it's behaving correctly within the context of the whole cluster.
Time is the next great deceiver. In a single computer, the quartz crystal on the motherboard provides a reasonably consistent clock. But in a distributed system, every node has its own clock, and they all drift. Even with NTP, the network time protocol, clocks can be off by milliseconds or even seconds. This sounds minor, but in a database, if node A thinks it's 10.001 and node B thinks it's 10.000, and they both update the same record, the last write wins strategy might discard the newer data because of a timestamp error. To solve this, engineers use logical clocks, like Lamport timestamps or vector clocks, which track the causal order of events rather than the wall clock time. In the distributed world, before and after are relative concepts, not absolute ones.
One of the most terrifying failure modes is the cascading failure, often triggered by a thundering herd. Imagine a service starts to slow down. The clients waiting for a response eventually time out, and following a simple retry logic, they immediately send the request again. Now, the already struggling service is hit with double the traffic. It crashes. The load balancer then shifts all that traffic to the remaining healthy nodes. These nodes, now overwhelmed, also fail. Within seconds, a small hiccup in one corner of your data center has wiped out your entire infrastructure. This is why advanced techniques like exponential backoff and circuit breakers are essential. They allow a system to fail fast and stop the bleeding before the entire cluster collapses under the weight of its own retries.
To understand the trade-offs we make, we have to look at the CAP theorem. Formulated by Eric Brewer, it states that in the face of a network partition, which is inevitable, a distributed system can only provide 2 of 3 guarantees: consistency, availability, or partition tolerance. Since partition tolerance is a requirement in any real-world network, the choice usually boils down to consistency versus availability. Do you want your system to always return the most recent data, even if it has to return an error when nodes can't talk?
Or do you want it to always return some data, even if it might be slightly out of date? There is no right answer, only trade-offs based on what your specific application needs. A banking app chooses consistency. A social media feed chooses availability.
This is where things get mathematically beautiful and incredibly complex. Algorithms like Paxos and Raft are designed to reach agreement even if some nodes fail. They work by using majorities. If a leader can convince a majority of the cluster to accept a change, that change becomes permanent. But what if the network splits exactly in half? Or what if a node is lying? These algorithms are the backbone of modern databases like CockroachDB or etcd. They turn the chaotic, random nature of independent machines into a single logical source of truth. But they come with a performance cost. Every agreement requires multiple round trips of network communication.
Sometimes the randomness isn't in the network or the logic, but in the environment itself. In a multi-tenant cloud environment, you have noisy neighbors. Your application might be running on a physical server shared with a crypto miner or a massive data processing job. Suddenly, your CPU cache is flushed or your disk bandwidth is throttled. Then there's the stop the world garbage collection. In languages like Java or Go, the runtime occasionally pauses the entire application to clean up memory. If this pause lasts 2 seconds and your heartbeat timeout is set to 1 second, the rest of the cluster will think your node is dead. It will trigger a re-election and move traffic, all because your node was just taking out the trash. These environmental stutterings are the ghosts in the machine that make distributed systems so hard to debug.
When these failures happen, standard logging is useless. If a request travels through 5 different services and fails in the 6th, looking at the logs of just one service won't tell you why. This is why we use distributed tracing. Every request is assigned a unique trace ID that follows it across every network hop. This allows us to reconstruct the entire journey and see exactly where the delay or error occurred. We also use chaos engineering, pioneered by Netflix with tools like Chaos Monkey, to intentionally break things in production. By randomly killing servers or injecting network latency, we force our systems to prove they can handle the inevitable. If you don't test your failure handling in a controlled way, the universe will test it for you at 3 a.m. on a Sunday.
In the end, the goal of distributed systems engineering isn't to build a system that never fails. That's impossible. The goal is to build a system that is resilient. A resilient system accepts that failure is the default state. It uses timeouts to prevent hanging, retries with backoff to prevent congestion, and circuit breakers to isolate faults. It uses consensus to maintain order amidst chaos, and observability to shine a light on the dark corners of the infrastructure. Designing for distribution is a shift in mindset, from building a single sturdy bridge to building a vast, self-healing web. The randomness isn't a bug, it's a fundamental property of the world we operate in. When you embrace the chaos, you can build something truly unstoppable.